So this is a very brief recap of the morning lecture, and the idea was really to introduce the idea of random numbers and look at some uses of numbers. So the key learning outcomes are knowing the difference between a random number and a pseudo-random number, to talk a little bit about randomness. We're going to finish with a big point about the importance of random allocation and random sampling, and somewhere along the way we're going to pick out the idea of Monte Carlo methods and very briefly mention the law of large numbers. So the ideas really want to take out of week. So the first thing is to point out that what we get out of a computer when we generate what we call a random number is actually a pseudo-random number. I gave one example of the kind of algorithm that does it in the lecture, but the point was to say that it's a deterministic system. So if we use the same start points, we're always going to get the same stream of random numbers. Something, if you become more computational, you might get interested in is the idea of blocking, where you add some natural source of randomness, possibly in the interests of speed. You do this to supplement a pseudo-random number generator. So the advantage of a pseudo-random number generator, though, is that if you set this seed, if you always get the same stream of random numbers, that's a great way for debugging any computer technique that involves random numbers. And in order for us to use a pseudo-random number, we actually need to use something called a test suite, or somebody needs to use a test suite to validate that what comes out of a pseudo-random number generator is good enough to regard as random numbers. So the key idea here is the idea that a computer algorithm nearly always gives us something, a pseudo-random number, and not a true random number. But we hope, for our purposes, it behaves as well as a true. Now, the interesting point is that once we've been given some uniform random numbers, and we've been doing this in Excel by typing equals rand, that gives us a uniformly distributed random number that's anywhere between 0 and 1. So there's two ideas that we want to clarify here. And the first is we're going to look at something called a discrete uniform random number. So if we think about rolling a die, we're going to get any of 6 numbers, and by the naive definition of probability by symmetry, we expect any of these to happen with probability 1 over 6. There are 6 outcomes. The probability any one of them happens is 1 over 6. So if I draw this as a probability model, I'm saying if I roll a die, I expect any of the outcomes to happen with probability 1 over 6. If I superimpose a computer-generated 100 die throws, we can see that sometimes the relative probabilities are a little way away from the expected probabilities. This is the idea of random error. We don't expect to get exactly 1/6 of the die rolling evenly. If we increase the simulation size, I now roll 500 die, I find that the proportion of die throws that are 1, 2 denoted by the grey bars are getting closer to my theoretical probability. And by the time I've rolled 50,000 dice, and I certainly did that with a computer, you can see that the grey bars denoting the proportion of rolls that were 1 or 2 are indeed very close to the blue lines that are denoting the probability of 1 over 6. And this is something that our intuition tells us, but it's formalised mathematically by a law of large numbers. And to be very formal, we've set the law of large numbers out here in mathematical notation, but it's telling us that the sample mean gets closer and closer to the population mean as we increase the sample size. If you're going on to study maths, there's some notation you can unpick later, but it formally sets out our intuition. Intuition, it tells us that it's better to work with a large data set than a small data set, and of course if we're using the kind of simulation techniques we're playing with in the lab, if we're simulating random variables, and that's cheap because computer time is cheap, we can get more accurate estimates simply by increasing the number of simulations. So, two consequences of the law of large numbers that matter to us for now. Now here's an interesting extension of the die throwing. Now we'll throw two die, and as we know, there's only one way we can get 12, and that's by rolling a 6 and a 6. So we now have 36 different outcomes. So the probability that I roll 12 is given by 1 over 36. Turns out there are 6 ways I can get a 7. I can roll a 2 and a 5 and a 2, a 3 and a 4 and a 3, 6 and a 1, or a 1 and a 6. So there are 7 possibilities in my 36 outcomes. So by the naive definition, I'm saying the probability of getting a 7 is 6 out of 36. The whole point here is any one of these events individually has a probability of 1 over 36, but when I look at the total, a pattern is beginning to form. And again, if I do a reasonably large computer simulation, tells us here I got slightly more 2s than the model would have expected me to get, and I got slightly less 5s as denoted by the grey bar, but the blue lines denote the probability model. 1 over 36, 7 over 36. And the whole point here, there is actually quite a strong mathematical pattern. So, the key idea, randomness, is not to do with an absence of pattern. When we roll two discrete uniform die, they combine and they give us quite a shape. Part of the goal of statistics is to match shapes we see in data to these kinds of mathematical patterns. Well, I've said what randomness isn't. It isn't a lack of pattern, but the English dictionary doesn't help. One of the definitions it gives as random is that something that has no specific pattern, but that's not what we mean here. Interestingly, the definition also tells us relating to event in which all outcomes are equally likely. I don't like that definition. It's implying that if I have a blood sample tested for some dread disease, they're using the naive definition, I have a 1 in 2 probability of having the disease. So we need to be really careful here. Our definition of probability is going to be given by this definition here. It's an event that is described by a probability distribution. Rather circular definition, but we have to remember we're working with a very precise definition of random, and we really do need to be careful to ignore some of the definitions we find in the dictionary. If we do a quick recap on some of the things we were doing in the tutorial, what we were doing, we were generating continuous standard uniform random variables, take on any value between 0 and 1, and we were applying a transformation which gave us a standard normal, and then having created the standard normal, we shifted and scaled the standard normal to get a slightly different normal. So there's a process going on. We have a computer algorithm that generates pseudo-random numbers that are uniform, and we can transform them to something that is more useful. How do we use them? We could use random numbers in Monte Carlo methods. This is what we were doing in the tutorial. Random numbers crop up in all kinds of computer algorithms, such as quicksort. Really important in cryptography. And just a little note there, apparently the NSA have a backdoor into this random number generator, and what that means is apparently they can read SSL traffic on the web if they want to. Random numbers, also a mathematical tool that help us understand probability, and of course you won't be surprised to find they come up a lot in statistical method. What we're looking at here is part of the IPCC report, and IPCC is the International Panel on Climate Change, and we're looking here at various scenarios that they have proposed as to how global warming may develop over time. And the key thing to note is not only do we get a forecast of what might happen, but we're getting an estimate of the uncertainty. So here, these scenarios overlap. Best case and worst case scenarios overlap. How have they produced this estimate? They have all kinds of models that tell you what's likely to happen, but then they've added Monte Carlo simulations to account for all the uncertainty in their projections. So it's an illustration of a really high profile and critical application using Monte Carlo. We're not going to do anything quite so complex. What you're very likely to meet is something to do with A/B testing or a variation on that. Good example for this, you compare two or more versions of your website, your game, your medical treatment, and the idea is you allocate subjects to one or other groups at random. And this is happening all the time on the web. You'd be surprised how often you visit a website and the particular web page or images you see have basically been determined under the hood by a pseudo random number generator. That decides which image, which web page you see, and then we can compare systematically whether there is a different pattern in the click-through rates, for example, of people who saw the B site rather than the A site. And the key that makes this work is that the A and B treatments are offered at random. Also, random sampling is really important. If you're wanting to understand a survey, it's vital you use some kind of sample taken at random. You can complicate the sample by working with strata and so on, but the key idea is if you want surveys to work, you need to select subjects at random. Two massive applications of randomness, all hidden in the procedures, but you need random allocation of subjects in controlled experiments such as A/B testing. This is really well described in SuperCrunchers, and you need to apply random selection in survey samples. Not particularly mathematical, but clearly the algorithms that generate the random numbers, as we've discussed, have to behave as if they were true random numbers. And these are perhaps two of the biggest ideas in statistics, and yet it's kind of hidden early on in the study process and something we take very much for granted, but vitally important and easy to miss.